All right, somebody tell us where we left off, or what did we do last time? Hopefully somebody has half a memory. Actually, before we do that, what is the central crisis at the heart of astrophysics and cosmology that we are going to continue to explore the ramifications of? Somebody in the back. Yes, Kansas.
I can't answer that question, but I can answer what we were going to look at for.
All right, I'll get back to you in 1 second. All right, we'll come back to you. Was it Sarah? You had your hand up too? Eh? Central crisis? B, you got it. Is the sun a liquid or a gas? Yeah. Maybe it's a solid too. Maybe at the center. That's a good question. That is the central crisis. Okay, so why does it matter? Who cares? Anybody else? Come on. Yes, remind me your name again. Natalie.
On that, right?
So fusion actually is the word. So the star, how it powers itself, is thought to be by a process that we can't seem to pull off on Earth, called fusion. What's that? Fission is actually when the atoms break apart. So big, heavy atoms tend to break apart naturally. We use it for nuclear power here on Earth and all sorts of horrific weapons. But we haven't been able to pull off this fusion stuff to any useful degree. So we can do some fusion. They've been doing it for about 100 years now in very small quantities. It's very expensive energetically. You don't get as much back as you put in, not even close. However, I did come across something. Actually, one of my friends sent me this the other day. I thought you guys might enjoy this. So this is, all right, so if you go and you become a scientist, I know none of you guys will, but if you do, you have to ask the government for money to do research, right? They give you money, half of it goes to the university for God knows what, the other half goes to paying for your lab and everything. So the way you do that is you got to write a grant proposal where you go and ask the government for some money. Every year, the different government agencies put out calls for grants. So they say, hey, we're interested in funding whatever, underwater basket weaving or whatever. This is one of the main granting institutions. It's actually the research elements of the Department of Defense here in the United States, one of the biggest funders, which is a bit ironic because you might think, like, why do I need to go to the military to get money? But they have the most money. So I actually got a lot of money from DARPA when I was doing my PhD too, even though I was studying, nanoscale mechanics of water molecules. We somehow framed it in such a way that it fit into one of these grant calls. And this is from this year. It just came out, actually. This is a new category that the Department of Defense is requesting grants for, which I thought was really interesting because it concerns the type of fusion we talked about last time, which is in solid metals, which is in some sense a very similar mechanism that we would propose for the liquid stars as well. In other words, you confine really tiny, really small atoms like hydrogens inside the layers of the metal, and then you use the entire tension of the material to squish the atoms together, which is a lot easier. It can be done at room temperature. I probably can't read this thing, but increase the rates of nuclear fusion in solids at near room temperature. Should investigate innovative approaches. Blah, blah, blah. Basically following up on a kind of known mechanism that was presented in the paper that I briefly referenced last time. So that's kind of cool, actually. So it looks like the government's interested in getting people, they're spending some money on it this year, which is pretty cool. I don't know. Again, I said last time, what's the problem with replicating, even if we buy the liquid model of fusion, what's the problem with it? Yeah.
The sun's real big.
It's big, yeah. So, how do you generate power? You have to have a passive source of pressure to squish those atoms together. So even though we can confine them much more easily inside of a metal than we can inside of, say, a plasma that's really hot, it's very hard to control with magnets, getting the pressure to squish the metal is still the problem, as far as I can tell. So just finding passive sources of pressure is still going to be tricky. And so I really look forward to this. I mean, it's so promising. I don't know what's going to happen. But that's pretty cool. So I thought I'd show you guys that. Yeah, Emily. Just sheer force. You gotta so the way that they did it in the first paper that I showed you guys last time is they actually take a laser and briefly put a ton of power into the metal so it heats it, and it shocks it. It's sort of like that, and squishes the little hydrogens are already confined inside the metal, and it squishes them together and they fuse. The problem is that laser power is much higher than the amount of energy you get back out of the fusion process. Excuse me. So it ain't there yet, but it looks like people are going to be working on it, and that's pretty cool because I talked to the guy who was one of the authors on that paper, and he seemed like there wasn't a lot of attention going to it, and so this is an interesting change. Yeah.
If I'm not mistaken, fusion isn't the main reason for why we should care about the sun being a gas or liquid, right?
Yes. Let me just see if I can give somebody else a chat, because Kansas said that she had a reason why we should care about the sun. Didn't you? No. All right. I thought you did. Does anybody else know why else we should care about whether or not the star is a gas or a liquid? The stars, including ours? Anybody? We talked about this. What motivates it? Yeah, in the back. Pretty much everything, right? But why does that matter? Who cares? Yeah? Well, beyond that, let's assume that we figure that out. Yeah. I think that's probably the real reason, which is a hard sell. But I do think that it's actually the most important reason in a weird way. Can you say that again so everybody can hear you a little bit louder? Yeah, so that we live in a world that makes sense, and it doesn't make sense because somebody told you it makes sense, right? We don't want to live in an Emperor's New Clothes world. Are you guys too young for that fable, Emperor's New Clothes? We don't want to live in a world where somebody just says, accept that this is the way things are. We want it to make sense. We want to be able to explain how the stars work to our children, and have it make sense. It shouldn't be. It should be very, very complex, but it should be able to be described at various levels of complexity, including a very simple one that anybody could understand. Okay. Yeah, and why does that matter? Why do we need to live in a world that makes sense? Kind of said it already, but this is so important, guys. Guys in the back, ladies. Why do we need to live in a world where our science actually makes sense? Yeah. Yeah. Yeah, I would say that how do I put that? That's right, first of all. And it's important because science is a really interesting tool for us being able to all be on the same page about things, right? You can lay things out, somebody else can look at it, they can tell you if it doesn't make sense, and then hopefully you can improve your explanation. Yeah, it's really important, Anybody have thoughts on that? This is just so important. I'm just going to keep harping on it. Otherwise, Dante? Did you get your point covered? Do you think?
Well, I was inviting others to say it.
Appreciate it. Okay, so that motivates our discussion. All right, where did we leave off? We talked a bit about fusion. We kind of covered fusion. What else did we talk about? We just barely started into something else. Anybody? Haven't.
We talked about, I think we touched on the U plus square equation.
We talked about mass a bit too. That's important. We're going to keep circling back on the concept of mass. What is that word? Yeah, do you have a comment?
Yeah, I was going to say, when we end off, we're just starting like spectral classes.
Yeah, we're getting into spectral classes. Let's do that in a second. So mass, that's really important because it's going to come back to bite us in a second. What's up with this word mass? Where do we see it? In two different main situations. Does anybody remember? This is pretty technical. I don't blame you for not remembering this, but does anybody remember? There's two different situations that Newton identified where this word mass pops up. Anybody? One of them is sticking you to the ground right now. Gravity, yes, gravity. It appears there, and then what's the other one? Inertia, more specifically. But yeah, yeah. So So inertia and gravity both point to it. And inertia, of course, is the thing that makes objects difficult to move and difficult to stop moving, for that matter. So I sort of proposed a way of thinking about the concept of mass to you guys in terms of what it means that the atoms are doing to each other. Why would things not want to move, and why would they stick to each other? How can we think about it? Kevin? Friction, that's fair. But in particular with the atoms, what does it mean for atoms to be in friction with each other?
Honestly, it has to do with those like little pairs that.
Yeah. The atoms are, we can think of the atoms as literally stuck to each other, literally tied to each other. It's a reasonable way of thinking about it. So this concept of mass scales how knitted together they are, right? Now, that's going to matter a bunch in a second because we started into the spectral classes thing at the end of class last time. So the standard spectral classification system and how we basically end up telling an entire story about the whole cosmos comes down to one classification system that everybody has worked on. It's based on really just two things. And we talked briefly about one of them last time, which was the spectral class, which really came down to what? Color. And what does color tell us? Temperature. Yeah, exactly. So we have temperature, and what else can we see about, when we look at the stars, we can see colors. What else do we see? Abby? Yeah, heck yeah, luminosity. What does luminosity mean? It's a big word. Yeah, in the back.
Apparent brightness.
Brightness, that's actually true brightness. But that's important, because apparent brightness and true brightness are not the same thing. What's the difference? You got your hand up back there? All right. Kevin?
Apparent brightness is how it looks to our eyes, where incomplete darkness anyway. And the true brightness is how it actually looks.
Yeah, so why would something look brighter or seem less bright than it is? Distance. And stuff in the way, I guess, could do it too. So scattering effects, yeah, that could do it. But yeah, in general, we have to know the distance, right? So distance is tricky. Actually, telling the distance of things turns out to be a lot more complicated. So actually, what I want to do today, hopefully, is walk you through the way that the astronomers to this very moment have determined the actual luminosity, right? And then I want to talk about some problems with that too, because it might not be that simple. Now, we talked about some problems with temperature last time. Does anybody remember anything from that? So I guess we can jump ahead and look at some of these things, right? So when you look at the color that's coming off of a heated body, do the colors of that body always give you the right temperature? So the formula that gives you the right temperature was designed for a specific material called a black body, right? These really special graphites, these hexagonal carbon chambers that are perfect transformers of heat energy into light energy. All the heat goes into light, all the light can get absorbed into heat. They're perfect. And the reality of the situation is that most materials, like if I heated up my water bottle, it wouldn't actually glow at the perfect black body temperature, right? It wouldn't be right. So some of the energy, some of the heat energy could go where? On a star. Where else could the heat be as opposed to just in the light? Yeah.
When first saw was the atmosphere, that might not be right.
Could be. There's chemistry that could be taking some of the heat on. Yeah, in the atmosphere. Yeah. Yeah. So in particular, where's where do we see kinetic energy in the sun? Rotation's one of them. So the surface rotates at a different speed at different parts, for sure. Rotates faster to the equator. Where else? What about on the sun? What about on the surface of the sun? You guys remember? Yeah, in the back. Well, that's a good piece. Yeah, there's also these little bubbles, right? These convection things, right? That's a lot of thermal motion going on that isn't going into the rays that we assess the temperature with. Yeah. Little cells, yeah, the granules, right? So there's a lot of dynamic structuring that appears to be taking up some of that kinetic energy, and temperature is, of course, a reflection of total kinetic energy. So the temperature, we'll roll with it for now. We're going to roll with a lot of this stuff, but you need to keep in the back of your head that this is not perfect yet. We don't have a perfect way of knowing these things. Now look, in the gaseous sun, there's no such thing as structure. Structures don't exist in gases, and so none of these things really, play out in the minds of the standing classification system that we have right now. This will become perhaps even more of a problem when it comes to the other piece of that chart. So I'm just going to write it on the board. We're trying to basically make a chart where we can put the intensity of the luminosity, let's just call it L, and we want to put on the other axis the temperature of the stars. And we're going to plot something and hopefully get some sort of family out of them. So temperature, yeah.
Last time I remember you saying something about how the apparent temperature is different from its real temperature of the stars, and I forgot the explanation for that.
So that's the thing that I'm trying to get at here. Both of these variables have some problems with them in terms of actually being able to take a light and say something materially significant about it. One is that the temperature, when you look at just rays, unless you know the material structure of the actual body that you're studying, moreover, unless that material body is a perfect graphite lattice, the temperature that you get from that peak on the blackbody curve isn't going to be accurate. It's at least subject to being inaccurate, because some of that kinetic energy could exist in other motions of that material, like convection, right? Or even conduction, chemistry, things that you mentioned, right? So you could actually be losing kinetic energy that isn't going into the rays. Black bodies take all of the temperature. There's no convection in a black body. There's no conduction either. They're really crummy conductors, actually. So all of the energy is going into the rays. All the thermal energy is going into the rays. So the temperature is actually accurate for that formula with respect to the black body. So most materials aren't perfect black bodies, so the temperature you get off them could be flawed. The intensity could be flawed. And even if there's no convection, and there's not much convection in my water bottle, the intensity would probably be a problem, right? So the intensity thing is kind of where the rest of our story turns to next, because intensity is really, really tricky. Now, let's build that out a little bit. We'll get into it. Does the temperature piece make sense to you guys, at least? All right. Okay. So, originally, when people back in the late 1800s started working on trying to classify temperatures of stars just by color, they were using the hydrogen lines in the atmosphere of the stars to do this classification system. And so it made a lot of sense. It was just A, B, C, D, E, F, G in terms of the temperature based on the hydrogen lines, not from the black body curves, actually. This was revised when people started to actually study black bodies, basically, and realized you could get a temperature from the color of the surface. And the result was that they had to redraw the order of the stars that had already been classified, which leaves us with this completely insane temperature spectrum that, O, B, A, F, G, K, M, right? This is kind of like the QWERTY keyboard, right? You know how it makes no sense, like it's not in any particular order. It's actually, there's lots of theories about why it ended up the way that it did. Yeah.
Most one I've heard was just because because of how typewriters were engineered.
Yeah, people were typing too fast and they were jamming their typewriters, from what I understand. But obviously that's not a problem anymore. You're not going to jam your computer by typing too fast, but the convention stuck and we moved on. So it's kind of an interesting holdover, this classification system. This is actually pretty cool, though. It was actually developed by a number of women, mostly working at the Harvard Observatory around the turn of the 20th century. Why were women doing all of this work, actually. Yeah. They were at war. Yeah, there was a lot of war going on. They also thought that the women were too fragile to be actually in the observing room, which was open to the night sky. So they basically tried to pawn off a lot of the tedious calculations on the women. I believe they actually called them computers. That's where the word came from, for a computer, was these ladies at the Harvard Observatory. Just so happens that the ones doing all the computing happened to solve a number of issues, including the classification system. They were also the first to figure out that the spectral lines implied that the stars were basically almost entirely made out of hydrogen with a little bit of helium. So that was late news from this same group of women, which is pretty awesome. Okay, so yeah, the spectral classes, they actually extend beyond the red side. So our stars somewhere around here in the yellow area, stars actually go completely off the map. Now, what's kind of fun, yeah. It's a G-class star. Low G. Yeah, pretty run-of-the-mill, actually. So most of the stars are pretty small and cold, actually. Most of them are smaller than ours. Most of them are pretty red and dim. Yeah.
I always get confused because you say our stars like a run-of-the-mill star, but then like 90% of all the stars are red dwarfs.
It's sort of like in the middle. Yeah. It also, the interesting thing about this temperature classification is that you notice as the temperature falls off, we end up with this over here. Does anybody know what that guy is? It's a gas giant. Well, they're not gas. That's a good point. Well, they do have some gas in the atmosphere, but yeah, so now we understand these things. We call them Jovians now. They used to call them gas giants. Some people still do. Why don't they call them gas giants? Yeah.
Because, well, one Jovian is just Jupiters. And they aren't, we don't call them gas giants anymore because they're not made of gas. Yeah, I believe Jupiter and Saturn are both like liquid metallic hydrogen, mostly.
Yeah, so they think that the big Jovian planets like Jupiter and Saturn are actually made out of the same stuff that we're talking about with this liquid sun model, this liquid metallic hydrogen, right? Which is really, really interesting. So yeah, I don't know. We'll keep playing with the idea, but basically when stars get cool enough, we call them planets. So, put that in your pipe and smoke it. Think about that one over the weekend. What does it mean for something to be a planet versus being a star? Jupiters are made out of mostly the same stuff as stars, right? You get a little bit bigger than a Jupiter, we call it a brown dwarf. Yeah, Evan.
Would it be like a star radiates out heat and like has fusion happening that's going on? Does it?
It is the defining line, yeah. So if you want to split hairs and say what's the difference between a planet and a star, let's say brown dwarf, which is kind of the transition species, and a star, it would be whether it can fuse neutral hydrogen or not. So actually brown dwarfs do fusion, but they only fuse that heavy hydrogen that has an extra bit of mass, a neutron, by accounting. Yeah.
Why do they only fuse the heaviest hydrogen? Wouldn't it be easier to fuse the lighter?
The heavier ones are easier. They're easier. They require less crunch. Yeah.
What's your name?
Evan in the back, yeah.
You brought up heat radiation. Jupiter and Saturn radiate heat. If you remember, you showed us an image of Jupiter and Saturn in the infrared, and it looked kind of like stars.
Yeah, they're really beautiful. So if you guys Google a picture of Jupiter in the infrared, it looks very much like the surface of the sun. The convection currents are a little bit different because it's obviously in a different state of heat, for lack of a better word. And there's different chemistry too. So, what's really fun is that, well, I guess we'll have to break out a lot of these pieces as we get moved down the line. But what's cool is that a lot of the chemistry that gives us what we see on Jupiter can really just be understood in terms of cooling reactions, actually. So if you take all the stuff that's in the stars and you just sort of cool it down over time, you get a lot of the same chemistry that gives us the beautiful colors that we see on Jupiter and Saturn and everybody else. Yeah.
So if planets like Jupiter and Saturn are relatively similar, could they be a good way to peering into the interior of the sun since they're not as hot?
Well, they definitely could be a way of understanding stars a little bit better. So I think that the really tricky thing for us, there's a couple of catches to this. So, I thought you were going to ask, and it might be a reasonable question to ask, is Jupiter just a dead star that's run out of fuel? Your textbook doesn't think so. Why not?
Well, I don't think so because, we have this transition phase of the brown dwarfs first off.
What happens when a brown dwarf cools off, though, or loses a bunch of its atmosphere?
I would assume it becomes like a solid core.
Probably goes through a transition where it looks like a Jupiter first, actually. Maybe. I don't know. So the real question, yeah, go ahead.
The main reason is because the current textbooks model everything in the solar system as having been born and created out of the same stuff at the same time.
Yeah, maybe say that louder. That's exactly right. It's
The textbook models everything in our solar system, maybe aside from the sun, or including it, of having been born and created of the same material at the same time.
Yeah, all the planets and everything is supposed to have happened really, really fast, actually. So the current cosmology that we have, called the Big Bang cosmology, colloquially, tells us that the whole universe happens the geological equivalent of yesterday. It happened very quick, all at once. Everything basically happened once, really fast. These are the only galaxies that have ever been created, and all the stuff inside them basically happened once. I mean, some of the stars may be recycled because they burned out really, really fast according to this gaseous model. But basically, the long and short answer is there's no way Jupiter could be a dead star because there hasn't been enough time for a star to cool off that much. Now, if we're wrong about that, if this cosmology about time having started 14 billion years ago, which is, like I say, geologically yesterday, if that's not true, then we actually have plenty of time to cool off stars. And so we'll play with that a little bit as we keep moving forward. Yeah, Kevin.
This is all just on the assumption that everything we can see is everything that is.
Oh, it's based on a lot more assumptions than that. That is a good one, yeah.
Whereas there could technically be stuff that light just hasn't reached us yet.
Yes, yeah, absolutely.
Better telescopes and then seeing further and being like, oh god, the universe is billions of years older than we thought it is.
Yeah, so Dante is making a really good point. I want to make sure everybody in back hears that. So I have a buddy, he's like 65, and he remembers when he was in high school, the universe was only like 6 billion years old. But then they got better telescopes, and they were like, uh-oh, we can see further. There's stuff. It looks the same as our stuff. We got to extend the birthday of the universe. Now they keep doing this. Every time they build a new telescope, the universe gets older and older. So the question becomes, will that trend continue? When we build the next generation of telescopes, will the universe be older? How much older? Old enough for a star to cool off and look like a Jupiter? I mean, who knows? Maybe. Does the universe even have a birthday? I don't know. We'll take a close look at this Big Bang cosmology. It's really based on two main lines of evidence, and there's some serious problems with both of them. Yeah.
How long would be theoretically needed to reach this Jupiter stage?
I haven't done that myself. I have a friend who works on that kind of modeling, but we're talking about a long time.
I remember first term in fall you mentioned it being trillions of years basically.
Yeah, well, if you wanted to cool off a star to the size and chemistry of something like the one that you're standing on right now, it would probably take trillions of years, which is thousands of billions of years. Now, thousands of billions of years seems insane given the current cosmology where the whole universe popped into existence one day 14 billion years ago. But if that isn't true, then time on these scales is possible all of a sudden. And that's really, really interesting. Not to say that it's what happened. It's not to say that the Earth was necessarily this a much older object than it appears to be to us today, but it could have been if we remove those constraints. So that's kind of an interest. We're starting to touch on the guardrails of why the cosmology that we ascribe to constrains the stories we tell about even our own planet and about everything, really, which is really, really fascinating once you start to see it. And that's going to become more and more clear as we move forward, I think. All right, questions, thoughts? All right, so we have temperature, at least apparent temperature, and we can, we could chalk stars onto our map over here, spreads of temperatures. We said basically most of them are cool, a few of them are hot. The Earth's kind of in the middle of all of that, although most of them, the sun. The Earth. Yes, the Earth. We will leave the Earth out of this. The sun is kind of in the middle of that temperature range. It's yellow, glowing yellow. There are some that are glowing blue. So we need to tell a story about how bright they are, how truly bright they are. And that turns out to be a much, much more difficult ask than the color to temperature claim. Now, what are some ideas about how we could get the actual intensity of these things? I'm going to go back because I kind of outlined how I want to break this to you guys. Yeah.
Doing our best to limit how much obstruction is between the telescope and the star.
The obstruction that turns out to be less of a problem than actually knowing the size of the thing, right? So if I'm on a dark road at night and there's a light coming at me, how do I know if it's a semi-truck or a bicycle? How do I know the size?
The size of the light, I guess.
Well, light, it could just be a faraway semi-truck, right? Or it could be a close by bicycle, right? You don't know is the problem. You don't know. Well, parallax is a good way to figure out distance. We're going to talk about distance, but yeah, that assumes that, yeah. Well,
Finally, unless you try and assume the size.
if you know how big it is. How would you know how big something? How could we say how big a star is? This is what I'm trying to steer you guys towards. So, okay, I like that. And that is actually the best thing that we can come up with. So there's been a number of other attempts. By the way, why can't we just look at it and say it's this big or that big or whatever? I mentioned this last time. Yeah. Well, it turns out when you look at a star, yeah, go ahead.
A star that's like really, really far away is just really bright, then that can have something to do with rather than one that's just like it's a lot dimmer but it's closer, and they can look the same brightness, but the distance is what matters.
Yeah, and can you actually measure the angular diameter of a light?
I don't think so.
You can't do it, actually. It's really frustrating. So, you'll notice if you go out with a telescope ever, one of your friends has one, you can go and look at something like Venus, and you can actually measure, you probably don't have the tools for it, but you could actually see in your eyepiece that there's actually an angular diameter, that you could take a ruler and measure the width of Venus, right? But with stars, you can't do it. They're just bright. They're pinpricks of light. They're just sources of light. And you can't actually see how wide it is. This is going to become a really big problem for us. So we can't know the radius. The best thing we can do to know how big it is its influence on its neighbors, right? Now, okay, so this requires us to talk a little bit about orbital mechanics, which we did last semester, but let's come back to it. Another thing that people have tried, before we get to that, is our line broadening. Remember line broadening? We said if gases are under pressure, that their lines will spread out a little bit, right? The gaseous sun proponents in the 1800s tried to use this to justify how you could get that black body spectrum out of a gas, right? Because, well, maybe if they all spread out just the right amount and everything, you know, the gas is under pressure, hypothetically, you could get it. So, line broadening, you know, there was some hope that, well, if a star is really big, then its atmosphere is going to be under a lot of tension and pressure, and the lines from the atmosphere, the individual ions in the atmosphere, are going to have spectra that are blurred out a little bit, right? Which is a very hopeful idea. The problem is there's lots of things that can blur out spectral lines, right? I'm going to come back to this in a second. So, what's another thing that can blur out spectral lines? How about this? You guys ever heard of Doppler shifts before? When have you heard of Doppler shifts? Yeah.
I've heard of the Doppler effect for like sound.
Yeah, for sound. What is it? Do you remember?
Kind of like distorts it as it moves away. Like,
Or towards you, right? You guys, yeah?
I don't know what Doppler shift is.
Okay.
I was thinking it sounds similar to doppelganger.
Doppelgangers? Unrelated, I think. But, okay, so Doppler shift. You guys have all experienced this when you're driving, right? Probably with ambulances, right? So as the ambulance is coming towards your car, what happens to the pitch of the siren? Does anybody remember? Just think about it. Versus when it's moving away from you. Yeah, it gets higher pitched as it comes towards you. And then as it moves away, the pitch lowers. Whoom, 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 right?
Part of that is that the speakers on ambulances are pointed directly forward. So I experienced this today. There was an ambulance in Medford as I was going to an appointment, and yet one was right, you know, pretty far behind us, really loud. But then the moment we were right behind it, and it was driving her behind it, it was going on its way. It was really quiet. It was pretty quiet comparatively, and that's because all the speakers are pointed forward.
So I'm not too concerned with the intensity of that sound signal. I'm talking about just the frequency of it. So the frequency, as you can see, as this thing is moving, let's just assume this is sound waves in this case. This is our ambulance moving away. As it moves into the medium that it's traveling through, the waves pile up in front of it. They compress, right? And you get a higher pitched noise in front of it. As it's moving away, the medium's elongated, and you get a lower frequency pitch out of it. Now, the same thing happens in light, except it's more about the observer encountering more of those crests on the front end, versus on the back end, the observer's encountering less of them. So when it comes to pitch of light, what do we mean? What is this?
Does it shift color?
Color, yeah. So color is the equivalent of pitch for light, right? So the waves are higher frequency when it is what color? Blue. And the waves are lower frequency, they are red. So when something is coming towards you, the perception is that the light shifts a little bit towards the...
Red.
No. Like red, blue, I don't know. Yeah, think about it. As it's coming towards you, it goes up in frequency, right? Away from you, goes down. So it gets bluer as it comes towards you, redder as it's moving away. Okay, so this can be seen in the actual shifting of individual lines in stellar atmospheres. And as stars actually rotate, so something like this, where part of the star is coming towards you and part of it is moving away, the problem is that it blurs out the lines again, right? Because your lines are spread out just like they would be from pressure broadening. So pressure isn't going to be the best way for us to tell how big a star is at the end of the day. We don't really aren't totally confident in that because we can broaden our spectrum in a number of different ways. There's now to be chemical processes that can do this as well. Okay, so Dante mentioned orbits, right? We might be able to figure out how big a star is by how it's moving with respect to its partners. All right. Oh, by the way, this is a cool figure. I should have mentioned this earlier. This is kind of the amount of stars in each category. I kind of like this illustration. So you can see that, you know, sort of roughly by category, how many they are of each type. And this is, you can see that it's listed in terms of stellar masses. That's because the colors have been correlated to stellar masses. We'll talk about why that is in a second.
Just the mass of our sun.
Yes. Yes, that's right. Okay, so how do we figure out how bright things are? Again, you look up in the sky to try to figure out how bright something is. You can give it a brightness notation, which is actually just called the apparent magnitude. That's how bright it looks. The problem is it's a completely insane scale that was developed long before advanced telescopes. We actually have to make negative brightness because the reference points didn't fit onto it at some point. So this is a completely insane scale, and it doesn't really tell us anything like we went over, just like Owen mentioned a while back. We don't know how bright something really is. We just know how bright it looks. They're not the same thing. Now, in terms of the orbits, there was a proposal based on the gaseous sun that basically follows from our fusion discussion. The more stuff you have, the more massive a star is, the more fusion it should be doing in the gaseous model. I guess in either model, honestly. It's going to have more opportunities, right? There's more stuff there, more pressure squishing it together. And the result is that in theory, the more massive something is, the brighter it should be. Now, this idea was championed by this guy who's come up before, Arthur Eddington. Eddington is shown here on the left, actually, alongside James Jeans. Now, Eddington asserted this idea that, in some sense, luminosity should be proportional to the mass of a planet. This is based just on first principles. This is not something anyone's ever tested. It's just that the basic idea seems like it should work out. Now, can anybody think of any problems with this idea? A star should be as bright as it is massive. Yeah.
Because two things could have the same mass, but because of how their atoms are arranged, they can have completely different velocities.
That's exactly right. That's exactly right. Yeah. Yeah.
Look at Earth, Venus. Venus is way brighter.
Venus is closer to the sun. But yes. Yeah. But they do have very different properties, refractive properties and so forth. I mean, they literally have different substances. The water on Earth, the carbon dioxide on Venus. Kevin?
I want to say that size doesn't equal mass, so
For our discussion, let's say that it does, though.
there.
But yeah, that's a good point, right? It could be very massive and spread out. It doesn't necessarily mean how dense it is. That's true. And that's kind of getting back to what Dante was saying. The material properties often obscure the optical properties. Or I should say that material properties can specify the optical properties. So Dante mentioned the example of carbon black, right? Black carbon, so graphite or something, and diamonds. They're both made out of pure carbon atoms. The only difference is the lattice structure, which you might think of as the crystal structure, but it's really the arrangement of the atoms inside of the material. The only difference between diamond and soot and graphite, the only difference is the arrangement of the atoms inside of it. Totally different optical properties. So if you were looking at a piece of heated graphite versus a piece of heated diamond, and you were doing it from the back of the room, you wouldn't even see the diamond, actually. Let alone would you be able to tell me the mass of the diamond based on the amount of light coming off of the heated thing, right? It's a terrible, terrible black body, actually. So this is a problem, but it doesn't matter for the gaseous star proponents, right? It doesn't matter to them because they don't have to worry about the material structure of the bodies themselves. I'm going to ask you guys again next time why this stuff matters. In addition to the sociological stuff and to the fusion, the reason that it matters whether the sun is a liquid or a gas is because the story that we start to tell really soon about what it means to see a bright or dim object in the sky is wildly different based on whether the star has structure, liquid, or solid, condensed matter structure, or whether it's just a gas with no structure that has no material properties whatsoever. Those are wildly different stories that you tell as a result of it. And we're starting to move into that territory. Does this make sense? Okay, so again, Eddington, super charming dude. This is, a totally reasonable assertion based on a gaseous model of the stars where there's no substructure. In fact, there's no emissivity to contend with at all. That's the amount of heat that gets turned into light. It's all turned into light. They're just perfect emitters. They don't worry about that at all. It's a reasonable assertion. And of course, James Jeans was his contemporary who was arguing for the liquid model. And Eddington really championed the idea of fusion for the first time. Does anybody remember what Jeans was championing? This is obviously before the Harvard computer ladies. Yeah.
Fission, mostly.
Yeah, radioactive decay, right? He thought that the stars, this is before they knew that the stars were hydrogen and helium mostly. So he thought they would be these big, heavy elements that were decaying. So he was wrong about that. And he sort of slinked off into the corner and surrendered this fight. So that's why I showed both of these guys on the screen. So this is the kind of holy grail. If we can know the mass of the stars, which we should be able to figure out from their orbits somehow, we'll talk about how we do that. If we can figure out their mass, then we can probably figure out how bright they are, at least because we know the mass of our star. How do we know the mass of our star, by the way? You just said it.
Because of its impact on objects of mass that we do know.
Yeah, from orbits. Yeah, so we'll review some of that for most of you who weren't even here last time. Okay, yeah.
So it's specifically because we know the mass of something like Earth, and then the sun's like gravitational impact on Earth.
Exactly. So that little dot with the ring around it, that's our system, our sun. Yep. So we know the mass of our star from the way that the bodies around it move. We know the mass of the bodies from the way that the little bodies move. This all gets very complicated. But we've studied the gravity on Earth quite well, which means we understand the mass of the Earth pretty well. And so we can work backwards from that. So this equation relates everything to what we can study in our own solar system. That's why there's a denominator that involves our luminosity of our star and our mass of our star, which are known quantities, right? It's a totally reasonable idea, actually. The problem is that it ignores the possibility that there's actual material structure in the stars which might affect their brightness, sort of like the diamond in the soot example that I just gave you. Yeah.
So, if we're getting the mass of the stars from the bodies around it, such as planets or asteroids, how do we determine the mass of stars that don't have any bodies near it?
Yeah, that's an excellent question. Actually, we can't even really, certainly when people started doing this kind of work, trying to plug things into this mass-luminosity relationship, they couldn't see planets around other stars at all. That's been a really, really recent phenomenon, like last 10, 15 years. Really, really, really multiplying more and more. What's that? Really recent, yeah. It's kind of crazy. That was a huge piece of our puzzle last semester when we were looking at our solar system, is that the story we told about our solar system, about all solar systems, was based on our solar system. And we only recently realized that our solar system is basically nothing like most of the solar systems we see. It's a very strange, diverse, yeah, it's a very, very weird solar system. Let's put it that way. Yeah.
So the thing I just missed what you said. What happened in the last 10, 15 years was us being able to see the planets.
Other stars, planets, yeah. Yeah, and there are some really good pictures. A lot of that is inferred by changes in brightness to the stars. So in other words, it's getting kind of yanked around, or there's a planet that passes in front of it. Some of them are actually very beautifully seen from above, where you can actually see some of the bigger planets orbiting the star. The brightness one's a little sketchier, because we're going to think about some ways in which brightness might be altered by things periodically that have nothing to do with planets passing in front of us. So anyways, you can't see planets on other stars back then when these people started working out this classification system that we're trying to do. So what did they use? What did they use for orbits if they couldn't see planets? They used other stars, right? So turns out almost all stars occur in pairs, at least. Sometimes 3, sometimes more. Pairs. This is really interesting because our star doesn't appear to have a partner, but it appears to be one of the few stars that doesn't have a partner, which is really, really weird. This is a number that keeps going up and up and up and up too. More and more of the stars are found to have partners, many of them dim partners, which we'll talk about, which are, variably given names like white dwarf, neutron stars, and so forth. Yeah.
By a dim partner, does that mean like a main sequence star would have like a white dwarf orbiting it, or each other?
That's it. Yeah, so we're gonna start talking about white dwarfs here in a minute, don't worry. They're an important piece of the puzzle. Neutron stars, these things are names that are given to let's say, stars that appear to be very massive, but very dim. Perhaps even hot and massive, but very dim, right? Okay, so we can look at stars orbiting each other, because most stars are orbiting at least one other star, sometimes more. Yeah.
So you're telling me that Tatooine is more realistic than Earth?
Yes. Well, realistic. It's more. It's characteristic. Let's say it's more representative of the whole. Yeah. So, binaries we call them. We're going to stick to just pairs because trios are very difficult to understand. But we can look at pairs of stars. It's actually the simplest orbital system imaginable. Now, theoretically, if we can see how two stars are orbiting each other, then we can see how much they're pulling on each other. And since we already basically agreed, I'm going to assume we agreed on this, we agreed that mass basically represents how hard something's pulling on its neighbor, particularly groups of atoms like stars are pulling on each other, then from the orbital mechanics, we can figure out the mass. Now, some of these binaries you can actually see because you're looking at them head on, from the top, so you can actually see them rotating each other. It's called visual binaries, and that's really nice. There's a couple of those, but most binaries aren't visual. They're aligned not quite perfectly. So we have to look at the spectrum to actually get the motions of the bodies. I'll walk you through how we do that. But the basic idea, and this is some stuff from 500 years ago that was quite brilliant actually. As soon as we had this model for the solar system where the sun was pulling on all of the planets and they're kind of being whipped around, they're basically on chains being, swung around the star, people started to really reformulate what it was about those orbits and what we could learn about them. And one of the first things that was set up was this essential relationship. This is works of Kepler and Newton combined in this sense, honestly, where let's say the radius, the width of the orbit had some proportionality to how long it took to go around. And how long it took to go around the orbit was scaled by the amount of material there, right? this makes sense. If there's a bunch of stuff, it's all pulling on each other, it's going to have a lot more freneticism to it than if there's just some beach balls floating around barely tethered to each other. Yeah.
What does D and P mean in this equation?
So P is the period. That's how long it takes to go around. D is it's an axis of the ellipse, but we can kind of think of it. It's kind of like it's similar to the concept of a radius, right? It's kind of how wide the ellipse is, right? It's actually not. It's something like the radius, but it's for an ellipse. There's two foci in an ellipse, and we're talking about one of the axes in that ellipse. Yeah. So you can think about it just in terms of period, how fast something goes around, how wide it is, and that's going to be scaled by how much stuff is there. So they figured this out with respect to our solar system. This is the famous Keplerian plot, right, where as bodies go around, they sort of come in close at one of the foci of the, I keep wanting to say parabola, of the ellipse. They speed up, and they move through each one of these sections in a very similar, each one of these wedges that it passes through has the same area to it and takes the same amount of time. So it goes faster at one end of the ellipse than at the other. Yeah.
Like gravity's pulling this in, and we're constantly like, why are we stuck on these orbits? Why is it not like a drain or like actually getting closer?
Well, because you're moving at tens of thousands of kilometers per second. You're moving really, really fast in that radial sense, right?
Isn't it also because the solar system is not still, it itself is orbiting? Is that part of it?
Well, if I understand the question, it's like, why isn't everything just getting gobbled up by the sun, right?
After a long period.
Yeah. Well, I mean, first of all, there's probably a fair amount of that that happens. Particularly, the question really becomes, how long has our solar system been here? You know, do planets spend time in different solar systems? Do they fly off the leash sometimes? Do they get captured sometimes? Or is it this very fast story we have to tell where everything happened yesterday and we have to make all the planets in place right where they are because that's all that we have time for, basically? You tell very, very different stories based on whether you have this Big Bang cosmology or you have something much longer. Let's just go with much longer. I'm not even gonna, let's say the limit of much longer is eternity. The other limit is the Big Bang was a few billions of years ago. And you have to make everything happen really, really fast. It's really, really fun because you can actually, so I know a guy whose entire job it is, he works at University of Bordeaux in France. He's an astronomer there. His entire job is to simulate weird situations. So, you know, he'll do fun experiments like how close would a star have to pass by our solar system to steal a planet? Or, you know, what would happen if we had a partner star and then we lost it? Which planets would it take with it? And it's really, really fun. So the answer is that you can make a lot of these things happen, right? You can have your planets get eaten by the star. But in the system we're living in right now, there's a really nice balance that's been struck. Maybe it's been struck just by selection, natural selection, essentially, very similar to like the Darwinian concept, right? So the planets that were not going fast enough to counteract gravity, they got eaten by the star a long time ago. The ones that were going too fast, that gravity couldn't hold on to them, they're out of here. And then only the ones in the perfect Goldilocks zone, the ones that are left that we see today, they're perfectly balanced in their outward velocity versus their inward pull of gravity. All right.
Yeah, I think part of this is that when you're explaining an orbit, it's not just that something is going around in a circle. It's that it's consistently, if say this body was not actively moving forward at some speed, it would just fall straight to the sun.
Yes.
Basically.
Yeah.
But because it's moving, it has momentum. By the time that it is being pulled, it's being pulled like if you've ever seen those like people who do like shot put with like a rope
It's
and
hammer throw.
hammer throw, yeah, like swinging around and around until right this right, and then they they can let go and suddenly it's the opposite direction, but still it's them moving and then while being pulled down.
It's actually really, really hard to throw something at the sun. So we were calculating this last weekend in San Francisco. We were originally thinking, the holy grail for us would be to splash something into the sun and take a picture of it splashing into the sun. Why is it so hard to throw something at the sun? Because the Earth is moving so fast in its forward velocity. So you have to stop all of that motion. Think about it. If the Earth is flying, I don't know off the top of my head how fast the Earth is moving in a radial velocity sense, but it's moving really fast, right? If you want to decelerate something to go straight to the sun, it has to stop all that forward motion. That's really, really expensive for a rocket to pull that off, actually. So yeah, something could naturally over time have its orbit degrade, right? If, something took up that momentum from it, collisions, dissipative processes of any sort, I don't even know. I mean, it would presumably take a long time. Yeah.
Yeah, Earth. I just looked up. Earth's moving about like 66 to 67,000 miles per hour.
Miles per hour, okay. I said kilometers per second. Kilometers per hour, miles per hour. Yeah, thousands, tens of thousands of miles per hour, right? So if you want to actually stop moving forward and get to the sun, you got to reverse that 60,000 whatever miles per hour motion that your rocket's just going to have just by being attached to the Earth system. It's really, really hard to do, actually. So that's a challenge. Not impossible. So we can use other orbits like Venus and Mercury to slow us down on the way. So it's doable, but it's tricky. Okay. Let's skip through some of this. So very early on, these early mathematical physicists, some of the first, basically figured out this formula. They realized that from the period of motion and from the expanse of that motion, you could deduce the masses of the bodies involved. So we can do that with stars too, and we look at the actual spectra of the stars. So we have to bring in that Doppler shift business I was talking about. So pick a line, any line, usually pick a bright line in the atmosphere of the star. And what we can see is that, let's say the black bodies of these guys are too smeared out. They're too continuous. You can't really track one star versus the other. But you can see how there are shared lines that are moving and intersecting because they're getting red shifted as they move away, and they're getting blue shifted as they move back towards us, right? And we can see two lines, one from each star, and they go, and they cross, and they intersect, okay? So from that, we can actually reconstruct a curve where we actually assess the velocity of that motion based on the Doppler shifts, and we track that across time. So if you have time and speed, what can you get as a result of that? Speed, time, and speed. You can get the distance. That's exactly right. So you can get the distance that that orbit is tracking out, right? And if we can get the distance of the orbit, we can get the velocity of, well, we already have that, obviously. If we have the span of the orbit, then we have some sense about how far away this thing is. And if we know how far away it is, then assuming nothing else is going to mess with its brightness, then we can say whether that thing that we see over there is a bicycle or a truck. Sorry, we have the mass as well. So we have the distance, we have the mass of it from its orbital mechanics, and we have the span of its orbit. So we know how far away it is, we know how big it is from the motion of these bodies with respect to each other. Now, what could go wrong? What could go wrong? See, this is, I think, a good GIF that shows you this idea. We got a little star and a big star that are
Just call it a GIF.
a GIF. What do you call it? A GIF?
It's a GIF.
A GIF. I'm sorry. A GIF. A little GIF here for you guys. Okay, so this is the basic principle that from looking at this thing, we can understand the size of the orbit. Oh, maybe it'll start up again. Bummer. I gotta hit it again. Was it maybe a movie, not a GIF? Go. Oh well. So what could go wrong with this is the problem, I guess. What could go wrong with this? So
Too many stars.
we know, we think we know the mass of it from this. Fair enough. Now, how do we know which planet's the big one still? Sorry, which star? I'm sorry. How do we know which star is the big one?
Do we look at the color of its light?
Yeah?
Assume that will be, that we look at which one is affected least.
Which one? How about just which one's brighter, right? Assuming that the radius has been measured. Should work. Should work. It should work really nicely for a star that has no structure, which means it has no material properties that would alter the brightness of its appearance, right? So what we actually do, what the gaseous astronomers do, is they say that the actual brightness in this pair corresponds to which one's bigger and which one's smaller. So the only thing that they have to change the intensity of two objects that are at the same distance from us is what? The radius. That's it. They don't have any other tools left, right? Because there's no way to affect the brightness of one of these ideal gas blobs other than shrinking it, right? So you have to make the flashlight smaller. That's the only tool they have left in the kit. However, if the star has structure, if it has actual condensed matter surface, if it has a liquid surface, then it has the ability to have wildly different emissivities, right? It can put out more or less light depending on how hot it is. Just based on rearranging a structure, just like the diamond and the graphite, you can get totally different optical properties as a result of the structure. That means that when we look out and we see that pair that we had in the last, one of them's brighter, let's say that blue one, and one of them's less bright, the red one, we don't know which one's actually bigger is the truth. We know that there's some mass distributed between the two of them. We might be able to see a wobble. That would be nice. So if we see a little bit of a wobble, we can say, oh, well, the center of mass is slightly offset in favor of this guy versus this guy. But we don't totally know the size of the things is the problem. Okay, so anyways, back to our standard textbook narrative. Standard textbook narrative doesn't worry about that. Says, okay, we know the masses of these planets. We've just assigned the mass to the one that is brightest, and we can assign a true luminosity. Planets, I keep saying planets and stars. Blurry line between the two, in my mind. Yes, it's actually funny. It's not my fault totally. So everybody called everything in the sky a star until very recently. This was, if you read any of the ancient astronomers, or actually the word planet really just refers to wandering stars. That's how they refer to them for most of time, because they move in strange ways compared to the rest of the stars. Planets, yeah, it's Greek. Yeah. Okay, so we can plot all of these things, which this is much to Eddington's eternal fame that this relationship can be constructed. We plot the mass of these planets versus their brightness, right? Now again, this is really, really fantastic for gaseous stars. It's a really, really convenient relationship that works, that in theory should play out really nicely. Again, the problem for us with liquid stars is this term E right here. Does anybody know what that term means? It's the emissivity. So it's how much light is actually transformed from heat into light, basically, right? So perfect black body, the emissivity is 1. So the luminosity of a perfect black body is directly proportional to the 4th power of temperature. Not so much with most real materials in real life. Probably not so much with our own star, and probably not so much with the other stars should they be proven to have actual surface with real structure to it in the bonded sense. So this could really mess up this entire pretty picture of mass and luminosity being directly related to one another. And this is going to matter a lot in a second. Okay. What else can we say? One of the ways we hope we could get maybe the actual radius of these things would be by looking at them going behind each other. This turns out to be halfway usable. Another way we could look at them going behind the moon and see how wide they are. So let's put this all together. These are basically all the pieces of the puzzle that we have so far. I just pulled this out of your textbook, I think, too. So we have apparent temperature. They say surface temperature. Sun's not even supposed to have a surface, so I'm not sure how they get away with that. Oh no, that's not good. Did I?
Turn it off.
It happens. It'll come back in a minute.
No, it's just 'cause I think it's just because the HDMI cable was faulty.
Good times. All right, so we have that. We have some lines in the atmosphere that we could use. We have luminosity, we hope. Maybe we don't actually have luminosity, but we think we do. We have radial velocity, rotation we talked about, which could easily be confused with pressure. Mass, okay, that's nice. We can get that from the spectroscopic binaries. And then some idea about radius for some of these stars from the way that they're obscured by one another when we look at them side by side. The result of this is that we can finally create this nice little two-axis system. And this is a diagram we're going to keep coming back to. So it's worth learning the name of, which is super easy. It's just called the HR diagram, which stands for Hertzsprung and Russell, who are these two scientists who put this all together. This is the lovely HR diagram. So, you know, we might hope that basically everything, you know, we'd probably have a much easier story to tell if on our luminosity versus temperature diagram, everything just kind of fit in a nice line, right? That would be nice. And then we could just tell a nice story about how everything just kind of cools off. It's born really hot and bright and just cools off, right? Like a fire. But you notice it's not quite that perfect, although it does have some elements of it. So you notice that most of the dots on this map actually do kind of cluster on this line. So there's kind of a curve to it like that, right? That's called the stars that we call those stars main sequence stars. But we also have two other pockets of stars that are very, very bizarre. They don't fit neatly into this story, or let's not even give it a story yet. They don't fit nicely onto our line. We got this pocket of stars over here, right? And what's up with these stars? Yeah, so what are they on this diagram? They're really hot and they're really dim. Hot and dim, right? Hot and dim. And then we've got another pocket of stars up here that don't quite fit onto the line. And what are these guys? The red giants, yes, red giants. And red giants are what? They are bright and cold. Sorry, this temperature diagram should actually go this way. I'm so sorry. Yeah. So temperature actually decreases this way. So these guys are actually cold and bright. By cold, I mean red. Yeah.
Yeah, the red super. Because I see two terms. I see like super giants and then just giants.
Depends on how big it is. They're still big.
Yeah.
They're big. They're really big, and they're cold, right? Okay, so you know, when we were looking at just the spectral information at the beginning of today, we were talking about how Jupiter could be fit onto that, right? And it's true. You could actually slide Jupiter in down here if you just extended this thing off forever. It would fit nicely as a very, very dim and very cold object, right? You could fit it onto that main sequence just way off in the distance. These ones are a little bit more perplexing, actually. And these ones have formed really the basis of the theoretical life and death story that we tell for stars going forward, right? Because we have to create a story for the lives and deaths of stars where they don't just simply cool off, right? For some reason, sometimes they're really, really dim and really, really hot. And sometimes they're really, really bright and really, really cold. That's the problem that we're going to be facing going forward. How in the world do you account for these two pockets and fit them into this story? Now, as you probably guessed by now, you got two very, very different stories based on whether these objects are infinitely compressible, right? If they're infinitely compressible, we can maybe make something that's very hot and very dim because we just shrink the radius of it. Whereas if they're not infinitely compressible, remember, liquids cannot be compressed essentially, right? Then we're actually relying on structure, optical material properties that result from structure to give us this. Likewise, over here, if we want to make something that's really cold and really bright, well, then we just have to expand something really big under the gaseous model, right? And now we have something that has a big radius, but it's cold. It's red and cold. Whereas, again, we have a different situation to explain. We have a whole toolkit of material properties in that lattice that can rearrange and give us something that is the wrong temperature even. Maybe it's the right temperature, but it's very bright still. Perhaps it's more bright than it should be. That could happen as well. Okay, so let's, I think we're going to move next into building out the story of how these things fit in, and eventually we'll work our way into telling a couple of different opposing life and death stories for stars. And each element of this life and death story is totally fair game for your guys' final project. I haven't put the syllabus up for it yet, but I want you guys to pick a situation that we've talked about in class where there's two stories to tell about something. One for the gaseous model, one for the liquid model. And so this saga that's about to unfold before us is a great opportunity. You could pick any elements of that. But hopefully we see a map, and we have to tell a story about what this map means next. All right, guys, have a good weekend. We'll do it again Tuesday.